Hello everyone, my name is Ben and I'm a Senior Developer Advocate for AWS Serverless, and I'm going to be talking to you about managing state in serverless applications. So we're going to cover three things today. First, I'll talk about how we define serverless at AWS. Then we'll look at some techniques and patterns that we've seen our customers using for managing state in their serverless applications. And finally, we'll touch on how to orchestrate state with serverless workflows. Now, I think it's really important, first of all, to recognise that everything I talk about today and all the architectural patterns that I show you are really in service to these fundamental goals. We want to enable teams within larger organisations to be able to build valuable features for their customers and do it in a way that's reliable, resilient and scale, and to be able to do this as fast as possible. So these are the four tenets that define serverless as an operational model. First, there should be no infrastructure to provision or manage, so that's no servers to spin up, nothing to operate or patch, no physical or virtual container orchestration of any sort. The service should scale automatically by unit of consumption rather than by unit of server. There should be a pay-for-value billing model. You could call this not pay for idle. It means that you only pay for the execution duration rather than by unit of server. And finally, there should be built-in availability and fault tolerance, so there's no need to architect for availability because that's baked into the service. So when we say serverless, we mean it's the removal of server operations, and that's the important distinction for our customers, because it means they are able to focus on the building of their application rather than the management and scaling of the infrastructure that application sits on. So that brings me to AWS Lambda, and Lambda is a serverless product that sits at the center of a few different trends and terms. You might have heard of event-driven compute, or function as a service, or serverless function as a service. And Lambda is all of these things, and it's serverless in that it fulfills our four qualifiers. Lambda lets you run code without provisioning or managing servers. So you pay only for the compute time that you consume, and there's no charge when your code is not running. With Lambda, you can run code for virtually any type of application or back-end service, and all with zero administration. You just upload your code and Lambda takes care of everything required to run and scale your code with high availability. Now, Lambda doesn't just sit in a vacuum. It will usually form part of a serverless application, typically with 2 or 3 components. You have the event source, the Lambda function itself, and the destination for the function to connect to. The event source has a number of services that can direct and interact directly with Lambda. It can be a change in database state, an upload to an S3 bucket, or a request from an HTTP endpoint. The function itself provides a curated execution environment with various languages built in. And now with the runtime API, you can bring pretty much any language that you're comfortable programming into Lambda. Then the destination can be whatever your code needs to interface with, and that's entirely up to you. It depends on the business logic and the requirements of your particular application. At the function level, there is a few interesting elements to take note of. The handler itself is the function that will be executed upon invocation, and there's a couple of parameters handed into that function. The first argument is the event object, and this contains information about the event in a JSON format. For example, an API request holds the HTTP request object. The second argument is the context object, which contains information about the invocation and provides methods allowing you to interact with the runtime and execution environment. You'll notice in this example here above the handler are the function's dependencies. You have configuration options, helper functions and so on. And here is where a function might initialize database connections, for example. Lambda is designed to run your code on demand in response to events. Now, if we look at the anatomy of a Lambda function, there's several different layers. So going from the outermost ring inwards, first there's the Lambda compute substrate, and that's the underlying compute layer for Lambda. Next, there's the Lambda service itself, which manages the scheduling and organization of workloads across hundreds of thousands of customers. And both of these layers are completely invisible to the customer and managed entirely by AWS. A little further up, there's the execution environment, and this is a customer specific and AWS account specific. It's a secure space where the code itself is run. In each execution environment, there's also a language runtime. Lambda provides a range of supported runtime languages, including Node.js, Python, Java, .NET Core, Go and Ruby, and you can bring your own runtime, as I mentioned before, with the runtime API. Finally, there's your function and the code that you provide to it, which is zipped up in a package with any dependencies that are needed. The execution environment and runtime is instantiated on demand for scale events, and the function is instantiated for every request. In this case, everything inside the handler is considered part of the function, and everything outside the handler is considered an initialization call and run along with any exec environment initialization. So, for functions as a service like AWS Lambda, they need to be stateless to provide the provisioning that enables serverless applications to be transparently scalable. But serverless applications themselves are generally still stateful in some way. When I talk about state, I mean in simple terms that a state can be defined as the condition of something at a specific point in time. And there's lots of different types of state, and we'll talk about some of them next. Also, statelessness has not been, it's not a new thing. It's been around since the beginning of the web. The HTTP protocol itself is stateless. The server treats all client connections equally and saves no information from prior requests or sessions. So a website that serves up a simple static web page is a really good example of a stateless model. The server receives requests for pages it hosts and sends the page data to requesting browsers. When an application operates in a stateful mode like this, the server keeps track of who users are and what they do from one screen to the next. Preserving the state of users' actions is fundamental to having a meaningful continuous session. It typically begins with a login or a user ID and password, establishing a beginning state to the session. As the user navigates through the site, the state may change, but the server maintains the state of the user's information throughout the session until they log out. And web applications have traditionally persisted identity through session cookies, relying on session IDs stored server-side. This forces developers to create session storage that is either unique to each server or implemented as a totally separate session storage layer, and this can add a whole different layer of complexity. So HTTP is a stateless protocol, and AJAX has worked because it never changed that. AJAX overcomes the stateless limits of HTTP by allowing the browser to behave as a semi-durable store. So using the AJAX approach, the browser loads just enough code to become capable stateful client, and then it controls the interaction. The server in this exchange becomes the stateless HTTP endpoint that it was always intended to be, while the browser is the semi-durable and stateful engine. Once the orchestration is done, i.e. the user closes the web page, it all goes away and HTTP remains a stateless protocol that it was designed to be. So functions as a service would do well to take an AJAX-like approach to this. Their statelessness nature can be respected as long as the supporting architecture that surrounds them is appropriate. So, for example, a token authentication is a more modern approach, and it's designed to solve the problems that session IDs stored server-side can't solve. Using tokens in place of session IDs can lower your server load, can streamline permission management, and provide better tools for supporting distributed or cloud-based infrastructure. In this method here, tokens are generated for your users after they present verified credentials. The initial authentication could be by username password credentials or API keys, or even tokens from another service. And this is stateless and easily scales. So, due to the stateless request-based nature of Lambda, any persistent state that is required by a workload beyond a single Lambda invocation must either be stored downstream of the Lambda function or returned to the caller by the function. So let's have a look at some of the different types of state and what we've seen our customers, how we've seen them solve this problem with some architectural patterns that you can also implement. The first approach here is for a stateless scalable authentication strategy, and for this you can use a Lambda Authorizer. The authentication mechanism here is similar to the sessions that we were looking at before, in that the user gets a token upon logging in and then sends that token back to the endpoint on every request. But JWT has a key advantage here in that it makes it easy to store additional user information directly in the token itself, not just the access credentials. On every request, the user will send one whole token to the endpoint, and if you store their username or access scopes in the JWT token, it will be very easy to access that information on every single HTTP request that you receive. You don't have to access the data store for getting user information, which can decrease operational costs significantly. So changing the shape of the data stored in JWT tokens during development will be much faster, and it enables easier experiments. Implementing JWT can be just plain easier than reading and writing sessions back and forth. The second strategy is to use a database to persist data, and this is best for semi-structured data where low latency and high throughput is important. But what kind of database model would be best for this? Typically, a key value model, the mode here is almost self-explanatory in that you store a set of values against a single key. And the design point for a key value store is that we can horizontally partition keys with almost limitless scale. And because we're using a key to look up one specific item, we can do that consistently with performance at scale. For this, we have a service called Amazon DynamoDB. It's multi-region, multi-master with on-demand pricing, so you don't have to provision any individual resources and you can pay for individual requests. So it's truly serverless in that respect. Now, if you have a particularly data-intensive app, you can further boost performance and still limit the number of requests made to the database by implementing this next solution, which is a database with caching. Now, this is ideal for semi-structured data where near real-time responses are required at really high throughput. You can use Elasticache to cache and read requests to a DynamoDB table and other database systems. So Amazon Elasticache works as an in-memory data store and cache to support the most demanding applications requiring sub-milliseconds response time. By utilizing an end-to-end optimized stack running on customer dedicated nodes, Amazon Elasticache can provide secure, super fast performance. It's a managed service that provides two different engines, Memcached and Redis, and you can add Lambda function to invalidate and update the cache whenever an object stored in a DynamoDB table is created or updated or deleted. The fourth strategy for large, long-lived unstructured data is to use a file storage system. And for this, Amazon S3 is ideal. It's object-based cloud storage for the internet, super durable and virtually limitless in terms of its storage capacity. So using a Lambda function to put or retrieve large customer record objects is ideal for unstructured durable data like this. A fifth technique is to use Lambda itself to store state between invocations, and this is okay for things like DB connections or object initialization. So the above execution model that we mentioned before makes Lambda functions effectively stateless, and this means that every time your Lambda function is triggered by an event, it's invoked in a completely new environment. So you don't have to access the execution context of the previous event, or you don't have access to that. However, due to the optimization noted above, the actual Lambda function is invoked only once per container instantiation. So if you recall that our functions run inside containers, so when a function is first invoked, all the code in our handler function gets executed and the handler function gets invoked. If the container is still available for subsequent requests, your function will get invoked and not the code around it. So for example, the create new database connection method here is called once per container instantiation and not every time the Lambda function is invoked. The handler function on the other hand is called every time your Lambda is invoked. This caching effect of containers also applies to the temp directory, and that can also be seen in the caching approach that we mentioned above. It's available as long as the container is being cached. Now, you can guess that this isn't a super reliable way to make our Lambda function stateful, and this is because you don't really have control of the underlying process by which Lambda is invoked or its containers are cached. Technique number 6 is to use an identity as a service provider as an intermission session store, and this can be helpful for smaller user session or session datasets. Amazon Cognito could be a good solution for this. It offers simple and secure user sign up and sign in with access control, and you can use like a partner service, for example Auth0, to save end user data in datasets containing key value pairs. And that data can then be accessed across logins and devices either directly using AWS SDK or via a Lambda function, for example. Now the seventh technique is to orchestrate, probably for business processes with durable medium-sized data. So we've been talking a lot about how to connect different services together, but there's also times when you may need more coordination than just a set and forget asynchronous messaging between your applications. So as we said, Lambda's functions are stateless and they're event driven and they exist in the cloud. But there aren't many apps with only one function or one entry point or one module or one component. So there's often been more than one function. And in fact, it will be common to have lots of functions and all of them talking to each other. And in fact, in applications, serverless or not, they tend to have a database. And in the cloud, you notice more often than not that they'll have some form of queue. And some of the Lambda functions might even connect to an external servers. And this is more like what we see as a modern serverless application. Now the question is, with all these servers, how do you connect and orchestrate the passing of state between each service? And for that, there's a fantastic service that we have called AWS Step Functions. Now this lets you coordinate multiple AWS services into serverless workflows so you can build and update apps quickly. You can design and run workflows that stitch together services into feature-rich applications. Now workflows are made up of a series of steps, with the output of one step acting as the input to the next. And building applications in this way as workflows, it's often easier to understand and reason about and explain to others. Building applications in this way also allows you to orchestrate and automate services with error handling, logic, parallel workloads all built in, and you can create long-running or high-throughput workloads. So you define your workloads in JSON, and you can visualize your workloads directly from within the AWS Management Console as you build out your JSON. And you can execute, monitor, and inspect your workloads from within the console too. Step Function supports 8 kinds of states today. You have task, choice, parallel, wait, pass, fail, success, map, and we have more states in the future planned, so look out for that. Task are the states that do your work. They call your application components and microservices, and there are 2 kinds of task states today. One pushes a call to AWS Lambda functions, and the other dispatches tasks to applications, which we call activity workers, when these activity workers then long poll for work. You also have the choice state, which allows you to introduce conditional branching and logic into your applications. We have parallel states that allow you to fork the same input across multiple states. And we have map states, which allows you to run steps for each element in an input array. So you can build really interesting workflows with a combination of all of these different types of states. Step function workflows are essentially a state machine with each task of the workflow having its own state, and it takes an input from the preceding state, processes it, perhaps with a service such as a Lambda function, and then outputs it to the next state. You also have some controls like input path, parameters, result path, and output path, which can be used to manipulate JSON as it moves through each state in your workflow. So step function standard workflows use a token bucket scheme to maintain service bandwidth. The refill rate for step function standard workflow is 1,300 state transitions per second. So if you think of it conceptually as a bucket of tokens, each time a state transition occurs, a token must be removed from the bucket, otherwise the action is throttled if no token is available in that bucket. So what if you require a higher throughput to prevent your orchestration workflows from throttling? Well then, you can use a step function's express workflow. And these are cost-effective high throughput state machines for event-driven applications. So express workflows are a newer AWS step functions workflow type. They cost-effectively orchestrate compute, database and messaging services into events at event rates greater than 100,000 events per second. So they're perfectly suitable for high volume event processing workloads such as IoT data ingestion, streaming, data processing and transformation, and high volume microservice orchestration. So what type of workflow should you use? Now, it can be totally reasonable to use a blend of both, and this is why express workflows can actually be nested into standard workflows. And this means you can use express workflows for short periods of task execution and standard workflows for long period tasks or tasks that require some kind of waiting mechanism. So the eighth and final strategy we see is a combination of all the different services that we've discussed, using step functions to orchestrate services along with DynamoDB and S3 to persist large long-lived data. So this approach here gives you the best of each service. You orchestrate state with step functions, express workflows or standard workflows depending on the kind of monitoring you require and the throughput that you need. And you can maintain information about the workflow in progress or about resources in that workflow with DynamoDB. And then you can store larger files in S3, passing S3 object reference along the workflow so it can be accessed or sent downstream to another service if it's required. So to recap, building stateful applications with stateless protocol is not a new thing. There's lots of different strategies to manage state with serverless applications, so be sure to pick a strategy that's suitable to the particular type of state that you need to handle. And you can build durable serverless orchestration workflows using step functions and a blend with other services such as S3 and DynamoDB for additional capabilities. Now, thank you very much for listening. If you have any questions that I'm not able to answer during this Q&A, please reach out to me on Twitter. My handle is Benjamin_L_S. And also, if you have 30 seconds to spare, please do fill out this feedback form to help us improve this presentation for any future deliveries. Thanks very much for your time.